Lewenkopf from Rio de Janeiro. Caio, the stage is all yours.
Oops. It's on. Ah, camera. Okay, so I'm fully loaded with all these devices. Good morning. So I thank the organizers for inviting me. I'm a little bit outside of the field. So basically, yeah, so I guess, oh, it's not working. No, it's not working. So is there a, no, the pointer. Is there a pointer? No. So I point with, I'm a tall guy, so I can, I mean, you should fix for the next one, I guess. I'm still a tall guy, so well, as I'm saying, I'm a little bit far away from the field, so, but I'll promise to you I'll speak about inhomogeneities and topology. And I'm kind of frustrated because I won't speak about strongly correlations here. And the materials I'm talking about are quantum, so that's fine. Oh, beautiful, that never fails. No, that's fine, so that never fails. Good, thank you very much. Yeah. Uh-oh. Oh, all these people, beautiful. So do I get 5 extra minutes? So if I get 5 minutes, I'm talking about the things you wanted me to talk about. This doesn't work either, so I'll go here. Okay, so since it's the first talk, I'm going to start with the real old stories and real basic things. So, and speaking about topology, I mean the precursors are basically this beautiful paper by Thouless, Komoto, Nightingale, and Denise, where they showed that the transversal Hall conductivity is quantized. And basically, at that time in history, people were actually looking at the edge channels, looking at the skipping orbits, thinking about a formulation based on Büttiker's ideas. And the beauty of this paper is that Thouless would stick to the Kubo formula and say, well, Kubo is able to describe the physics, and so we should get the real physics, the quantization by using Kubo. And he succeeded in a simple model where he could make some analytical analysis with some numerics and would show precisely what we know and the experiments have shown. So the next step is that 2 years later, there was this influential paper by Barry where he was studying something very different, you know, like adiabatic perturbations. And what happens if you perturb the system adiabatically and you close a circle, and then he figured out that expressed his theory in terms of geometrical phase, later on known as Barry phase, and was able to develop on the way some objects called Barry curvature, etc. And by an effort by some of these collaborators of Thouless, they actually noticed that the Barry curvature actually integrated over a Brillion zone would give exactly the same result as this famous Thouless, Komoto, Nightingale, and Denise paper. And so this was a beginning of an era trying to understand this conductivity effects based on topology. And actually many things happened over the years. And the next big precursor was this paper by Haldane a few years later, where he would study a situation, a model where you see the integer quantum Hall effect without magnetic field. And he proposed the tie-binding Hamiltonian that is now known as the graphene type binding Hamiltonian, with a mass term to open a gap, and some magic trick that would introduce some chirality to the problem. And this was a pure mathematical model, and he was able to analyze within this model the Chern number and the conductivity, and he will propose a phase diagram based on the intensity of the mass term and this chirality term, the phase that will accumulate. And he will show that basically, depending on the choice of parameters, you have some regions where the Chern number will be an integer, meaning the system is characterized as topological, and some other regions where it will be a trivial insulator. And to go from one region to another, you have to cross this line here and close the gap. And this is the phenomenology of a phase transition in this kind of physics, that basically, if you are topological and you go to a trivial phase, you have to change your parameters and go to a region, cross a boundary where the gap goes to 0. So this is the message I want you to keep in mind when I move on here. And this is based on a very simple model. And this paper was kind of a sleeping beauty. People paid little attention to it until Kane and Malley came and showed that you can double the dimension of this haldane, the spinless model of haldane, introduce a spin, introduce 2 copies, and eventually this magic term that will cause a topology will be a spin-orbit interaction. And this opened the way, a path to do some material science on that. And people over the years have understood the phenomenology of 2D topological insulators, where you open a gap, you form a Dirac cone, and in this cone, the edge states are the topological manifestations, and they are robust against disorder. This is important. In 3D, the situation is a little bit more tricky. Even this figure is kind of misleading. So you have actually, in 3D, you have a surface state, a 2D state, and it behaves more or less like a 2D electron gas. I mean, if you do the spectroscopy, you see very nice behavior due to these surface states about the spin properties. And if you try to measure things with transport, then instead of getting a quantized conductance, or conductance in this case, conductivity, you have something like resembles more a 2D, the physics of a 2D electron gas, and the physics of anti-localization. And these experiments are hard and unconclusive. So I'll stick to the 2D case for a while. And if you are interested, I have some few slides about 3D, but I guess there won't be time. Now let's move to experiments. So the situation in experiments is, I can summarize more or less like the following. So very early on, people were able to produce systems which exhibit this 2D topological behavior. These were the quantum spin Hall states. And in this particular case is a quantum well. The details are not so important for this talk. And this paper is highly cited, is a first example. And later on, this very same group was able to show that these states really are edge states within the topological gap. They probed the nature of these states. They show they are quite robust. But if you measure the conductance, then what happens is that within the region where you expect this nice topological behavior, and you expect a very quantized conductance in terms of E square over H, you see something that gets very close to it. Over there it's clearer, but it's not like quantum Hall, Well, it's, you have all these wiggles, and it never gets really a precise quantization. And the second feature, which is also very important, is that you only observe this for very small, very short systems. If you go to longer systems, the tendency is to really suppress the conductance, and the systems become trivial or almost trivial topological, trivial insulators. So it's a little bit frustrating, but there is an army of theorists that tackle this problem, and there are hundreds of papers where people propose different mechanisms to explain that. Before I go into that, let me just flash one other example. So there are other examples in different material platforms for that. And this is a very nice paper where people extended this to TMDs and these transition metal dichogenites. And in this particular case, you see that the same pattern repeats itself. So you have these small wiggles around the quantized value. It's never as precise as being a, like metrology standard, like the quantum Hall. And as you and for longer devices, longer channels, then the system tends to localize. So it's a very universal thing, and it shows that these edge states are not as protected as theorists or the naive theory would predict. Okay, so what are the mechanisms to explain that? So first of all, the idea is that you have these helical states. So you have a spin, let's say, down the blue line propagating one direction, spin up propagating in the other direction in one edge. And this state to be destroyed, to cause backscattering, you either need to flip the spin, or you need to have some inter-edge scattering, right? Otherwise, you cannot really, unless you play with the spin, you cannot really backscatter. So if there is no spin flip, people were thinking about percolation mechanisms. And the idea is that if you put sufficient disorder in this system, then you have all these localized states around. And eventually, you can activate and jump around, and you destroy the quantization by just hopping from one localized state to the other. And this could be done by thermal activation, for instance. Since the systems are still rather wide, this mechanism has been discarded in the early days, but now the theorists are reinvestigating. Apparently, the Würzburg group has this as one of their favorites. But there is little theoretical support for that. The Würzburg is a group of the experimental group. The other one has attracted more attention, and the idea is that the simplest thing is to flip the spin is to introduce some magnetic impurities. That's easy. But the thing is that the experimentalists have control on that. And they will actually say, well, our concentration of magnetic impurity is so low that we can discard that. The other, then there's a bunch of papers, 10 or so, where people would come up with a very intricate mechanism involving phonons, and, but it has the wrong temperature dependence. Then there are other groups that claim that you can add Rashba interaction, and this will actually, in this Haldane plot, will push the transition outside the experimental reach. But again, this is hardly true because the coupling constants are too large. And it looks nice, but probably it's not what explains. Then this was a very popular one, charge puddles and many body effects. You have charge puddles in the substrate or somewhere else, and then the electron will jump into these charge puddles, will actually do some spin flip, and eventually a backscatter. Unfortunately, has the wrong temperature dependence also. And then there is one that's one of my favorites. It's nuclear spins. They are there, unavoidable. They are tiny, but they are many. And this is under discussion. Most of the theoretical studies that has been done so far are no really good simulations. They use they assume that there are many nuclear spins. They do a bosonization for the one-channel case, and they discuss everything very qualitatively, but there is no length scale, prediction for the length scale where you localized so far. And then we actually wrote a small paper with non-magnetic disorder, and this is 5 minutes to advertise that. This is I have done with former student of mine, and the idea is that if you have one of these TMDs or graphene or one of these guys that has these hexagonal lattices, then if you put a vacancy, introduce a vacancy in the system, you create a localized state. Well, if you have a localized state, then actually, to Stoner, you can think of creating a magnetic moment, right? So eventually, you have you have to pay the price to charge it, and this has to compute the kinetic energy. And so what we verified is that within this very simple model, you actually do get some suppression from we put in one edge, so the backscattering is only one edge, so it's still it's not 2 times E squared over H, but just 1 time. And it occurs only in 2 very narrow resonances. This is very unphysical. And this is due to the fact that you have this single resonance. If you put more single vacancies, if you put more vacancies, then eventually you populate with very many narrow resonances, but this is not what the experimentalists see, and vacancies are really rare in these materials. So what we explored is something else. We introduced some edge roughness, which is typical in these TMDs. And then what happens is that you put a very random sequence, but once in a while you have a few zigzag edges, a few zigzag aligned, and zigzags, well, there's a vast literature on that. Terminations cause some localized states, and then we can see that if you have very short ones, then you have a small suppression of the transmission, and you have a long one. Once you hit a long one, then you have an entire suppression. So that would be suggesting that we have an interesting mechanism to explain why short systems still do exhibit almost quantized conductance, but with fluctuations, small fluctuations, and longer systems eventually localize. Okay, so let's shift gear and go to strong disorder, the main subject here. And strong disorder is a problem. Why? Because everything I told you so far is based on an integration of the Berry curvature, for instance, over the Brillion zone, right? So strong disorder implies you don't have a Brillion zone. So you have an absence of translation invariance, and then does the theory actually make sense? Is the theory perturbative theory? What is the nature of this theory, right? So you actually formulate in terms of a topology, but then you keep asking yourself microscopically what happens. And then this paper come up that really triggered our attention to it. It's a PRL 5-6 years ago. And these guys, they actually took a random lattice. They called an amorphous material. This is not an amorphous, it's a random lattice. It's a gas, right? And locally, they introduced a tight binding model that resembles locally the Haldane model. Okay, so it has variable, the hopping matrix elements, they die out with with distance between sides, but locally, provided they are short enough, they resemble the Haldane model. And they computed it. They made a lot of simulations, and they see the two main features of these 2D topological insulators, namely the edge states, right? They are formed. And there is a region where you have a perfect quantized conductance, right? So this is a numerical result. They try to justify in different ways, but the question is, what is then the topological invariant? There is no, how do you characterize? Do you have a deeper understanding on that? And this is the question we were puzzled. One question, the other issue is, can we actually produce such a system in the lab, right? And so the first contribution of our group was to team up with some people with a lot of experience in band structure calculation, and we're inspired by this system, which is bismuthane, which is a realization of a 2D system that has topological properties. And, well, this is an experimental system, so these guys worked very hard to anneal the system and produce a very clean system and observe edge states and etc. And then we were proposing that we just de-anneal. So we do the opposite. So we start with a model that we borrowed from people in StatMac. We actually started flipping the bonds, and then there is a full DFT calculation that you relax the system and do this generation after the generation and study the properties of such a system. Well, the results are in two papers that we published over the years. And they are summarized here, that if you compute the transmission or the conductance in such a system, then you see that there is a region where the conductance is quantized. There are edge states, so these are the helical states. And depending on the amount of amorphization, you even have the chance to drill holes and have localized states inside the system building internal edges. So this is the result of the simulation. More interesting is that our approach is based on some stroboscopic or amorphization step. And so we can monitor the band gap as a function of the amortization step as the system gets more and more amorphous. And then the band gap, I mean, it's hard, you know, like it's DFT, so you don't have a lot of realizations. So this is the best curve we could produce. And one of the critiques on our early paper is that people were asking, well, what happens if you proceed with this amorphization procedure? Would it eventually go into a trivial insulator or not? And then with realistic parameters, we see that to the best of our simulation, the system seems to die, to close the gap, but then it recovers and stays constant. And it means that in the amorphous phase, the system is a topological insulator. We could compute all other indicators there, but well, if somebody has interest in this, I can discuss. Then we did something that people from ab initio hate, right? So there are some infiltrated people, and so we played with parameters. So I asked them, what happens if you play with a spin-orbit interaction? Make the spin-orbit interaction smaller, and then eventually you close a little bit the gap, and then you amorphize. And the answer is that eventually if the spin-orbit interaction is sufficiently small, then you close a gap at some given amorphization step, and there is a phase transition, and the system never recovers. So we computed the Z2 with a trick that I don't want to go into detail, but this is actually the result. So you need a large gap. So if you want to look at some materials, you need a large gap in the pristine phase because all this degrades this gap, and if you don't have a large gap, you don't survive. Okay, so the idea here is this. So what is the picture that Haldane taught us? Is that two states are in the same topological phase if they can smoothly be transformed into each other without closing the gap. Unfortunately, our model is not smooth. So this is a definition which is nice for mathematicians, but it has no predictive power for us. So we cannot forehand tell you when you would close or not. And as long as you stay in one of these paths, you are always topological, right? And you be, here is a situation where you start topological, you go to a trivial, and you end up topological again. You have two phase transitions. So, and this is our first work trying to improve on that. We developed a small model where we were, disorder model, where we could go smoothly from the ordered phase to what people call a paracrystal, and eventually to the amorphous one. And this will be the diffraction pattern. You see that here you have sort of a ring structure, which is characteristic of amorphous. You know the nearest neighbor, the distance, but you know don't know where it is, and here's some intermediate. And we were studying that, and basically we took the half BHZ model, taking just one edge, and depending on this parameter that drives the system from topological to trivial, then for the clean system we have a kind of a Haldane plot, and for the disordered one, the simulations indicate that you almost close the gap, right? You go to a region where it seems that you are expected to close the gap, but since it's a finite size kind of system, you go from one Chern number to another, and well, you're expected to close, but here it's not very clear. But what we show is that you always have the chance to stay topological. And there are some explanations on that based on the self-energy. So this model is too complicated, and so we decided to investigate something else and basically look at some Chern number in real space. This is an interesting theory that was put forward many years ago. It's basically a Fourier transform of the formulation in a reciprocal space. And then you have these local markers, and with these local markers you can tell in real space what is if the system is topological or not. And so there's a lot of work on that, including some people in the audience, which worked on that as well. And this is a nice paper where people analyze the BHZ model, the one that describes these experiments by Würzburg, by basically playing with the mass term. And they see some phase transition. They were able to compute some critical exponent, and looking exactly at the same physics as Haldane, but looking at the phase transition. So what happens if you introduce disorder? And so we take this BHZ model again, and we introduce some Anderson disorder. And basically this is a paper 15 years ago where people show that you can drive a topological phase by disorder. And if you crank up sufficiently disorder, then the system which starts as a trivial insulator becomes quantized. There are edge states, and eventually it moves away. So we were playing with that to understand or to characterize the phase transition in such a setting and using these local markers. And then there are a few surprises here. First, well, the first is that actually there is some universal behavior, and we're able to find some critical exponent. But then we're very disappointed because the local markers, they are not really quantized, right? If you look at some disordered systems, then you have some surprises, and I'll show you what happens. So this explains this width, which corresponds to the variance of the local markers. But we understand, we characterize some critical exponent, and we can motivate the power of this critical exponent looking at the effective mass. This is the thing. And we looked in different systems. We looked at the BHZ, the Haldane model. We looked also at the Kane and Mealy, and so it's always 2, surprisingly, for disordered systems. And this is the bad news. The bad news, or, well, it is what it is. So if you look at these local markers, if you have a clean system, like this one, this BHZ, so if you look at exactly at the center, you have a perfect 1, which indicates this local Chern number is 1. But the integration over the whole system is 0. So it has to be compensated by the edges. This is the property of this proposed local Chern number. And if you put disorder, you see this nice figure here, which shows that you have a lot of fluctuations. In some pies, this local Chern number is larger than 2, and at the edges, it's very concentrated to compensate and give you the integration equal to 1. So it's a quantity which has been proposed based on something that was constructed in reciprocal space, and not from a real genuine theory based on real space. And then it has some drawbacks, and these are the drawbacks. But we can play with that and understand that in this phase transition, it fluctuates more. And this is part of this work that we are finishing with Gerson and Brian. So the summary is that what I presented to you is a summary on this, that the theory of topological insulator is based on band theory for topological insulators, based on the integration over reciprocal space. And then when you have strongly disorder, then you have to come up with some different ideas. And the idea is, how do you describe this metal insulation transition is one of the open questions. And the quest for a bona fide real space topological invariant is still open. And then looking at, like in these Marvel movies, and upon request of José Hoyos, there is a spoiler. When you give the credits, then there is some spoiler. And this is an ongoing investigation, and it points out to something very interesting, which is, this is a collaboration I have with people in the math department in Regensburg. And basically, when you asked some mathematician what is the approach he would like to use to describe this topological things, he would say, well, these are too complicated. We use a K-theory where you map the topological properties into some K functions that have a much simpler structure. And in this way, they had some success, for instance, in shedding some light on the Atiyah-Singer index theorem and other things. And applying, and these guys taught me that applying one of these particular algebras called C algebra, rho C star algebra, then you reproduce the symmetries of the Altland-Zirnbauer classification and actually the correspondent for topological states, right? These other papers. And this provides you also a recipe. It's not only pure math. It provides you a recipe how to compute these indices. And unfortunately, I don't have anything to show you for disordered systems, but we can recover the phase diagram for the Kane-Mealy problem based only and exclusively on real space properties, a tight binding model formulated in real space without referring any time to go to K space. And this is what gives us hope to proceed, and if I come here next year, I report on that, Jose. So he asked me to do this, and I don't have enough results so far. Okay, thank you very much for your attention.
Thanks a lot. Questions? Okay. The birthday guy first.
Can you explain how this works? The real space thing? I mean, in terms we understand.
Well, in a nutshell,
what do you calculate? Maybe it's easier if you.
In a nutshell, this guy here, based on a tight binding model, right? So you can use these tricks to establish some algebra, and you map this tight binding model into an algebra that can be represented by a determinant, and this determinant has some terms that you can easily associate with the Hamiltonian, and some others that have a very complicated structure. And then once you compute this determinant numerically, right, then you get either an invariant or not. So this is more like a working thing, but these things which are not easily associated to the Hamiltonian are the ones that actually contain information about the topology. So this is, I'm sorry. The thing is, so these guys were satisfied with the first half there. and my contribution was to tell them, look, you have to compute things to convince the physicist. And then we applied this to different models, clean models, and it works. And they were saying, well, it's a theorem. So I was happy. They didn't understand my happiness. But now they are computing also for, we are computing also for disordered systems, where it shows that you have to really go to large matrices. So this is the thing that we still don't understand, the convergence, what is at stake, etc. And so they are excited again, because even having a theorem, you have to work hard to extract things. So that's the status of the thing.
Rafael.
Caio, so,
Hi.
So if you go to something less dramatic as amorphous, like a quasi-crystal,
Yeah.
And you can do, the usual approximants to get to the quasi-crystal, is it easier to understand? Is this better understood, or not really?
It's at the same status, because you lose the working tool, the standard working tool to approach the problem, because you all have, you can always pretend you can cheat, and this is, sorry, let me conclude. You lose the basic working tool. Now, what is the approach that people are currently using? Well, they think, okay, so I have a strongly disordered system, so I use a supercell thing. I expand a gigantic supercell, and I calculate everything at the gamma point. And then I say, well, okay, so with that, I'm happy, I'm a physicist, I understand everything. Well, yeah, but again, it's not very satisfactory. And with the quasi-crystals, this is the way people are doing things.
Here. Okay. So what about the bot index to characterize the topology of the system in the real state?
Well, it has also drawbacks. It's better than the trick I just described to Rafael, right? But from my perspective, right? From the theoretical perspective. But if you actually want to compute this bot index, then it has some issues about convergence. You have to really take big chunks of your real space, and there is no real recipe to tell you how large are these chunks, or there is no understanding so far when does it converge or not. It converges differently for different systems. So we had some large experience on that for this amorphous, because this is the way we started. So again, it's better, but there are some open issues as well. But you're right, this is a better, superior approach. I mean,
All right. First of all, I very much appreciate the talk.
Thank you.
Mathematician, of course, that is super beautiful view of the world. And in that case, you definitely need a compact manifold to define topology, which would not apply when we have a real world and when you have disorder. So, so I certainly appreciate the fact that even if we don't have a cleanest definition of topology, many properties still follow, similar to a real clean topological insulator, right? So I think for physicists, this is perfectly fine. But what I don't quite understand is the following. If my disorder has a strength that exceed the scale of my gap, which protect the topology, which also in some sense protect the edge state from the rest of the world, wouldn't you have a problem that the edge state will also couple to the bulk state, and eventually you lose the real protection of the edge state?
Yeah, this is, you're 100% correct. This is actually what we see in different models. Thank you for the question. So this is, this is one of the things that we take an Anderson model, which is already some little, well, unrealistic, and then we take a strength that will put you out, and then you destroy everything. But even if you do some more realistic calculations by these DFT guys, then you see that the topological gap is here and start to degrade near the edges of the topological. And this is, fits into this scenario that you described. So once you have sufficient disorder to go outside, then that's it. So you kill it.
I have a quick question on what you mentioned in passing, namely the imperfect transport from helical edge states. So if I understood correctly, the thing you advertise, a non-magnetic disorder plus interactions, relies at its core by the fact that the vacancy on the honeycomb lattice produces a zero energy state, which then can become a local moment.
Yeah.
So is this mechanism then lattice specific? So if I would have a TI which does not live on a honeycomb lattice, would this be better?
Let's put the other way around. So this is specific for the honeycomb. I don't know if there are other lattices that exhibit the same. But for instance, for a square lattice, etc., it doesn't work. So rephrasing your question, this mechanism is, for instance, not applicable to these Würzburg experiments, to this semiconductors quantum wells, because there you discretize the model in a square well. This is applicable for TMDs, graphene with some adsorbed disorder, etc., etc. So you need, in this case, the specific hexagonal honeycomb.
And for mercury telluride, we need a different explanation.
Mercury telluride.
Yes, the square lattice.
Yeah, exactly. So I was very careful when I oh, okay. So when I wrote this paper, because people actually were reading it, thinking about mercury telluride. And we actually write in the abstract, this is good for TMDs. And there are 3 experiments on TMDs that see the same physics as in mercury telluride. Okay.
Unfortunately, you have to move on. I know there
Okay,
are
thank
raising
you.
questions, so you can talk to Caio later. Nice
Okay.
thanking again.
Thank you.